Okay, today we're going to look at solving trigonometric equations, and there's three main ways that we're going to look at this. We're going to look at it just solving an equation for the variable, using some algebra such as factoring, and then using some of our trig identities. How I'm going to teach this section is just by examples. So first we're going to look at solving equations. Now we're going to treat cosine of theta or cosine of x as our variable. And so to solve this equation, we're going to try to get our variable by itself. First thing we're going to do is we're going to add the square root of 3 to each side. And then we're going to divide each side by 2. Next, it becomes very, very important for you to know the unit circle. So we're going to ask ourselves, first, what reference angle has a cosine equal to the square root of 3 over 2? And our reference angle is the pi over 6, 30 degrees. Then you look at your unit circle, and you decide which quadrants the unit circle gives us a positive cosine. And if you remember that stating, all students take calculus. So cosine is positive in quadrant 1 and in quadrant 4. So I need to figure out this angle measurement. So to figure out this angle measurement, I have 2 pi minus pi over 6, which therefore will be 11 pi over 6. Part A, I want the answers in one rotation from 0 to 2 pi. My answer is theta is equal to pi over 6 or 11 pi over 6. But the wonderful thing about trig functions is they're periodic functions. So although I end up with a cosine equal to square root of 2 over square root of 3 over 2 at 30 degrees here, if I go all the way around and then back, that also has the answer. And if I go twice around and stop, that has the same one. So when we were asked to find all possible answers, we write our original that's in the unit circle from 0 to 2 pi, and then we add 2 pi k for every time we go around the circle, and k is understood to be some constant. Likewise, at 11 pi over 6, that gives us a solution, but if I go around the circle one time and then stop, that's the solution. If I go around the circle 5,000 times and stop, it's still a solution. So that's what we add on the plus 2 pi k. And that is all the possible solutions to this equation. Now let's look at our second example. Okay, in the second example, I'm also going to find the solutions from 0 to 2 pi and all possible solutions. So we're going to start the same way. Let's get the trig function on the side by itself by subtracting 2 sine of t from each side. And now let's move the square root of 3 over to the other side by adding it to each side. Divide by 2. And so now I need to figure out which reference angle has a sine equal to square root of 3 over 2. And from my unit circle, I know that sine is equal to the square root of 3 over 2 at 60 degrees. Or again, we're always going to write our answers in radians. That's pi over 3 radians. And then I go to my unit circle, and I figure out which quadrants I have a positive sine. So sine is positive in the first quadrant and in this second quadrant. So I need to figure out what that larger angle is. So to figure out that larger angle, notice this is pi, and I've subtracted pi over 3. So I just take pi minus pi over 3. Get a common denominator, and then we end up with 2 pi over 3. And since those are the only two quadrants where my sine is a positive value, those are my only two solutions from 0 to 2 pi. Now to find all possible solutions, I take my two solutions and I add 2n pi. Now notice this time I wrote it with the n. Sometimes you can write it with the n or you write in a k. It really doesn't matter what that variable is. Traditionally it's just an n or a k. So I could have wrote it as this. And again, multiplication is order of operations, so I can write this as 2 pi k as I did in the last example, or 2k pi as I did in this example. It really doesn't matter the order when you're doing multiplication. Okay, so again, we're going to start the same way. Let's get our cosines on the side together. So since this is smaller side, I'm going to move it over to the right-hand side. And then add 2. So I'm asking myself, when is cosine of theta equal to negative 3? So to do this one, that's not one of those special angles that we have memorized from our unit circle. So I'm going to look at the graph of cosine. And I'll just do one period. And hopefully you know that, and if we're going around our unit circle, cosine at, remembering cosine is the x values. So cosine at 0 degrees is 1. Cosine at pi over 2, 90 degrees, is 0. Cosine at pi is negative 1. Cosine at 3 pi over 2 is 0. And cosine at 2 pi is 1. So this is our cosine graph, and then that just keeps repeating and repeating and repeating. Now, I want to know, when is this cosine graph equal to negative 3? Well, negative 3 is down here. So this graph is never ever going to cross that negative 3. So this has no solution. So you have to be careful. Sometimes on our trig equations, there's no solution to the equation. So be on the lookout for that. Now I'm going to give you one to try on your own. The second method we're used to solving trig equations is by using some factoring, some algebra skills that we have. So if you have a trig function and they are in different degrees, so we can't combine these two together, what you're going to do is get the equation like you do a quadratic or a cubic, get it equal to 0, and then use some sort of factoring to solve. So I'm going to start by subtracting tangent of x from each side so I can get that equal to 0. And then factor after GCF, so tangent of x is in common. And as our rules of our zero product rule, once you get two factors set equal to 0, you can set each factor equal to 0. And then it becomes a problem just like we did on the last section. So when is tangent of x equal to 0 degrees? And from our unit circle or from our table of values that we have memorized, we know that tangent of x is equal to 0 at 0 degrees and at pi. And again, you get that from your unit circle. And I remember tangent is equal to sine over cosine. So I'm going to figure out sine, which is my y, divided by my x. So that simplifies down to 0. Here, my y divided by x, I'm dividing by 0. So that's undefined, so that doesn't work. 0 divided by negative 1, that gives us 0. And here again, we have negative 1 divided by 0, which is undefined. So that's how I get the answers at 0 and pi as my solutions for this first part. And then the second equation, solve for the tangent by adding 1 to each side, dividing by 3. And the opposite of squaring something is square rooting it. I want to know, when is the tangent equal to a positive or negative square root of 3 over 3? So again, first find my reference angle in the first quadrant. And tangent is equal to square root of 3 over 3 at pi over 6. So that's my reference angle. This occurs at pi over 6. And then I need all of the other quadrants, because it's either plus or minus, so every quadrant I'm going to have an answer. Every one of these that has a reference angle of pi over 6 is going to be a solution. So I'm going to have 4 solutions for this one. So x is equal to pi over 6, and then pi minus pi over 6, which is 5 pi over 6. And then pi plus pi over 6, which is 7 pi over 6. And then 2 pi minus pi over 6, which is 11 pi over 6. So part A, all the solutions on the interval from 0 to 2 pi are these 6 answers. So to find all my solutions, I can write this just like I did the last problem, and taking each of my 6 answers and adding 2 pi k. But that's a lot to write down, and that's very tedious. If I notice a pattern, for example, I notice that 0 degrees and pi are exactly pi from each other. So I can combine these two and simply write this as 0 plus pi k. Repeat every pi. I also notice that if I look at pi over 6 and 7 pi over 6, they form a straight line, so they're exactly pi away from each other. So I can combine those two together and write it repeating every pi instead of every 2 pi. Likewise, I notice that if I do 5 pi over 6 and 11 pi over 6, they form a straight line. So they differ by pi. So I can put those two together, and I can write all my solutions condensedly as three little answers, and it saves me a little bit of time. Either way is correct. It's just this is considered more formal. Okay, so let's look at our next example. I already have it set equal to 0, so now all I got to do is factoring. So let's take out a sine of x, which is our GCF, and again, set each factor equal to 0. Solve the new individual equations. First one's already solved for the trig function, and the second one, I'll subtract the 1 and divide by the 2. For my unit circlet, sine is equal to 0. Sine is my y value, so my y is 0 here and here, so at 0 degrees and at pi. And then to figure this out, first we're going to find our reference angle. So for my unit circle now, I'm going to figure out where I have a sine equal to 1/2. Don't worry about the negative right now. And that's at 30 degrees or pi over 6. So that's going to be my reference angle. Now I deal with the negative. I ask myself, okay, in which quadrants is sine negative? So sine is going to be negative in quadrant 3 and in quadrant 4. Or you can look at sine as the y values. In these two quadrants, I'm under the x-axis, so my y's are negative. So now I just got to figure out which angle has a reference angle of pi over 6 in each of these quadrants. So in quadrant 3, I take pi and add pi over 6 to get a 7 pi over 6. And in quadrant 4, I take 2 pi and I subtract pi over 6 to get 11 pi over 6. So in part A, theta is equal to 0 pi, 7 pi over 6, or 11 pi over 6. Now to find all possible solutions, again 0 and pi differ by pi. So I can either write that as theta is equal to 0 plus pi k or pi k. And then 7 pi over 3 and that, they don't differ by pi, so I'm going to have to do these separately. So that's going to be 7 pi over 6 plus 2 pi k and 11 pi over 6 plus 2 pi k. So those will be all of my possible solutions for example number 5. All right, the last one will involve us doing a little bit more work in which we have to use our trig identities that we've learned in the previous sections. So notice here I got sine of 2x, so I'm going to have to use my double angle identity to replace this. And I recall that sine of 2x is equal to 2 sine of x times cosine of x, so replacing that in, and that's equal to cosine. Now, like in the last section on factoring, now I need to get it equal to 0 by subtracting subtracting cosine of x from each side. Then I'm going to do my factoring. I notice I have a GCF of cosine of x, so let's take the cosine of x out. Using the zero product rule, set each of those factors equal to 0 and solve each equation. So I need to figure out when cosine of x is equal to 0, so that's when my x values are 0. X values are 0 at pi over 2 and 3 pi over 2. Now I need to figure out where my sine is equal to 1/2. Sine of 1/2 has a reference angle at pi over 6. And then which quadrants is sine positive in? Sine is positive in quadrants 1 and quadrants 2. Therefore, one answer is going to be the pi over 6. And I need to find the second answer by taking pi minus pi over 6. And I end up with my second solution is 5 pi over 6. So for part A, we have 4 solutions: pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. Again, pi over 2 and 3 pi over 6, they differ by pi, so I can combine those together and I write all my solutions and just do by pi instead of 2 pi. But these two are not different, they don't form a straight line, so I have to write them separately and add 2 pi k. And there's all my solutions to example number 6. Okay, I want to start the same way on example number 7. Set it equal to 0. Now, I don't have a GCF in common here, so I'm kind of stuck. When you're stuck, remember we write everything in terms of sine and cosine. I need to subtract these fractions, so a common denominator. Multiply each side by cosine of x. Now I have a GCF, so I can factor out the sine of x. Set each factor equal to 0. Solve each equation. When is the sign equal to 0? That's your y. Sign is your y. So when is y equal to 0? And that is at 0 and pi. Is your cosine equal to 1? So our cosine, which is our x value, is equal to 1 only at 0, because at pi is equal to -1. So our solution is 0 and pi. And again, 0 and pi differ by pi. So all my solutions is just pi k. Similarly here, I don't have a GCF, so I can't factor anything out. I've already have a set equal to 0. So let's replace cosecant x with an identity in terms of sine and cosine. So we're going to write everything in terms of sine and cosine. Get a common denominator so I can add these two fractions. Then multiply each side by sine of x. And then solve. Okay, now if you're very observant, you might see a problem right now. I have something squared equal to a negative number. When can something square equal a negative number? Well, it never can. So this is another example of a no solution equation.